Okay, on page 5, we're going to be looking for the domain of a function. And so this is what the final product will look like when you're done. You'll just simply put a 5 up here. And then in asterisks, go ahead and write this for now, but please note that there is not a lot of room here to write, so be careful whenever you go to do this. You can go ahead and put your foldable here just to see what it would look like. It says the x values that make a fraction's denominator equal to 0 may or may not be a vertical asymptote or a whole. That's going to be a note for later. I'll explain that more on page 6 in just a little while. So with this foldable, and in this video, we're going to be looking for the domain. Please remember from your Algebra 1 days that the domain is the input values or the independent values. So for the first one, we're going to look at from a graph, from a polynomial, from a rational function, and from a radical function. So those are the different ways that we're going to look for the domain. So I've now turned my interactive notebook over. With this foldable, you'll have to cut the sides out along the lines. You'll notice that I will also cut along these dashed lines here all the way up. And it's going to create 4 tabs for me, one for graphs, one for polynomials, one for rational functions, and one for radical functions. I'll be able to lift every single one of these tabs individually. So you'll also notice there's a couple of notes here. There's an asterisk. That rational function is going to go with this asterisk here, and that's what that note was talking about. But again, we'll discuss that on page 6 in just a moment. Please also number 1 and 2 for your g of t and j of k respectively. And then under radical function, there's another asterisk, but this doesn't belong to this same asterisk note over here. It's something completely different. And it says that these notes will be true for all even root functions, whether it's a 4th root, a 6th root, or an 8th root. You'll notice right now this is just for a square root. The index here, there's an imaginary 2 even though you don't see it. But this would be true if there was a 4, a 6, or an 8 there as well. So what we'll do is we'll lift up this first tab where it says I can find domain from a graph. So the first one that you're going to see here is that there are 6 dots. With these 6 dots, if I wanted to find the domain of them, I would just simply write the x values. These are the only dots on here, so these are the only points for this particular graph. So notice, for example, -1 is not being used. Nah, +2 is not being used, and so forth. So the only x values that are being used are the ones that are here at -5, here at x equals -2, here at x equals 0, x equals 1, x equals 4, and x equals 6. And you'll notice that's the same domain values that I put in here. This is going to be your set notation. I've got my little curly brackets, and I've got my numbers inside. We've got a second graph here. We'll talk a little bit more about vertical asymptotes on page 6 when we get there. But in this particular case, there's going to be a vertical asymptote right here. So when you have a vertical asymptote, this is actually never going to be attained. You'll notice that as we're getting closer and closer to the number x equals 1, it actually will never touch this point. These values actually start to decrease significantly, and these values on the right start to increase significantly as well. We'll talk about why this is happening, but the x value that this is occurring for is at x equals 2. It says to be careful of vertical asymptotes. And so you'll notice these blue lines have domain values at, for example, things like -3, -2, -0.5. They have one at maybe about 1.9, 2.1, and then so forth. So the only value that's not being used is this dashed line right here that's vertical. And again, this is called a vertical asymptote. So it's going to be restricted from your domain. This means that you can use every single other number except x equals 2. So if you remember your set notation from yesterday, this is your little squiggly brackets here. This x with a / means x such that, and it says that x cannot be equal to 2. So it's saying that it can be anything else it wants except for the number 2. All right, and then down at the bottom, the last example, it says to be careful of open and / closed circles and gaps. So if I'm looking at this graph here, you'll notice that there's a closed circle here starting at -5. Numbers like, for example, -4.9, -4.1, -2.1, all of these values are being used. Same continues if I go forward. These values are also being used. So you'll notice that I'm going to go all the way from -5 to positive 1. So the first part of my domain is going to be from negative 5 to positive 1. You'll notice this is interval notation. I have brackets on each end to represent these closed dots. And then you'll notice that these are x values. Negative 5 is the furthest left, and positive 1 is the furthest right. Now there's a gap right in here, and so I'm going to completely skip that gap. There's no x values being used. And the last one is going to be from positive 2 to positive 5. Now you'll notice that this is actually going to be an open circle now, and that's going to correlate with this parentheses that you see here on 2. All of the x values are being used from 2.1, 3.7, all the way up to the number 5. And then it's again a closed circle, so that's going to correlate with this bracket symbol here. Okay? When you open up the second tab, this is going to be for polynomials. There's some examples for polynomials on the front page of this tab. It says that all polynomials have no restrictions on their domain, which means that the values are going to be all real numbers. You can plug in any numbers that you want. So the first example on the other page was 2x minus 1. You can take any number, multiply it by 2, subtract by 1, and then you would still get a value for that. So that would be an example of a linear function when you graph it. So the domain has absolutely no restrictions. This first symbol that I have here is your set notation. It says that x is going to be true for the domain for all x, such that x is an element of the real numbers. You don't have to use this symbol here if you don't want to. You can write it out, x is an element of the real numbers, but it just simply means is an element of. These double-stemmed r's right here, there's two vertical lines here that represents all real numbers. I could put this in interval notation instead. This one was set notation. I could put it in interval notation instead, and all real numbers would simply be from negative infinity all the way to positive infinity for my x's. You'll notice I have two sets of parentheses because I can never attain infinity. Now, the range could be possibly restricted. It could be all real numbers as well. It could have restrictions, but it really depends on the end behavior or the graph. We'll talk about end behavior when we get to chapter 2. All right, when you open up the next tab, we've got two examples. One is for j of k and one is for g of t. Both of these are called rational functions. And these are like your fractions. So we have one set of restrictions for fractions. You can't divide by 0. So if ever you have a number divided by 0, this is considered undefined. So if I look at g of t equal to t plus 3 divided by t minus 2, if you look at the bottom, you know that t equals 2 would make this bottom equal to 0. What that means is that when I plug it in at the top, I'll get 5 divided by 0. This doesn't have a solution, so as a result, this would be undefined. But if I plug in other numbers, like for example 1, 1.1, 7.3, negative 100, any of those other values would actually give me a value for y, so there are no restrictions besides t equals 2. And so that's the way that I would write my domain. The values of t such that t is not equal to 2. Finally, on example 2, we've got j of k equal to k plus 1 divided by 2k squared minus 3k minus 5. We would do the same thing. We'd set the bottom equal to 0. You would factor this, and when you factor this, this would come back from your Algebra 1 days. You would have 2k minus 5 and k plus 1. When you multiply these two binomials, you would get back this polynomial. You want to make sure that this bottom doesn't equal 0, so you'll set each piece equal to 0 to see what value of k that will make that happen. So for this one, you'll add 5 and divide by 2, so that means k can't be 5 halves. If you plug in 5 halves into this, you get 0, which means if you plug in 5 halves into the original, you would also get 0 at the bottom, which is bad. Do the same thing for k equals negative 1, plug it into the bottom, and then you would still get another 0, which means the domain of this second function is going to be k such that k is not equal to 5 halves and k is not equal to negative 1. Finally, for your last tab, we have restrictions for radicals. If you remember from your Algebra 1 days, you can't have the square root of a negative number. So the square root of some negative number will have no solution. So looking at this first example 1, h of p, we've got the square root of p minus 4. For example, if I plug in the number 2 here, 2 minus 4 is negative 2, which means I cannot take the square root of negative 2. If I plug in, let's say, 0, 0 minus 4 is negative 4. I cannot take the square root of negative 4. So that's just two examples of numbers that I cannot use. So what we do is we look at the numbers that we can use. For example, I can use the number 5. 5 minus 4 is 1, and the square root of 1 is 1. That's an example of a number I can use. I can actually also use the number 4, because 4 minus 4 is 0, and the square root of 0 is 0. So if you look at the type of numbers that you're allowed to use, these are all numbers that are bigger than 4. And so that's what I've written. The values of p such that p is greater than or equal to 4. This is your set notation. And your interval notation would have a bracket on 4, comma, infinity, parentheses, and this would be your interval notation. One last example, this one's a little bit more tricky, and so it's going to be a little bit tougher. It says m of v is equal to square root of v squared minus 4. So for this one, I could try to plug in numbers. For example, if I plug in 0, 0 squared is 0, minus 4 is negative 4. You can't take the square root of that, so 0 is not part of your domain. If I plug in, for example, the number 1, 1 squared is 1, minus 4 is negative 3. Also, you can't take the square root of negative 3. So if I did this, it would take me a long time to find all of those values. So what I'm going to do is I'm going to take what's under the radical, and I'm going to take the radical part away. I'm going to write v squared minus 4 is bigger than or equal to 0. My goal is to figure out when will v squared minus 4 be greater than or equal to 0. So an example that would work would be 5. 5 squared is 25, minus 4 is 21, and you can take the square root of 21. So if I did it this way, it would take me a very long time. So what I'm going to do is I'm going to factor this. That would become v plus 2, v minus 2, and I want to make sure that this is equal to 0. So the first, is greater than or equal to 0. So the first thing I do is to look to see where it's equal to 0 first. For example, v equals negative 2 and v equals 2 would make these two statements 0, which means it would make the original v squared minus 4 0 as well. Now my concern is when this is positive. So what I'm going to do is I'm actually going to test around these points. I'll put them on a number line. I've got them circled so I know which 2 points I'm testing around. You'll pick any number to the left of negative 2, any number in the middle, and any number to the right. Now, let's check negative 3. Go back to the very original and see if it works. Negative 3 squared is 9, minus 4 is the square root of 5. It does work, so I put a check mark there. We tried 0 already, so I'm going to go ahead and put an X mark there because I know it's not going to work. And if I plug in positive 3, I'll get the same value of square root of 5, so I know that this one also works. So what this number line tells me is that no matter what value I pick between negative 2 and 2, none of the values will work. You can try it. Try x equals 1. Try x equals 1/2, and so forth. This number line also tells me where the values do work. Anything bigger than 2 and anything less than negative 2. If you don't trust me, try some. Try 3, try 4, try 5, and so forth. So now we have a number line that tells us all the values that do work. And so that's what I'm going to set up for my domain. It says the values of v such that v is less than or equal to negative 2, and the values of v such that v is greater than or equal to positive 2. Okay? And so that will be all for this foldable.